So we got all the way to 11.6, 11.7 is Archimedes' principle. And let's see here.
Are we going to finish off chapter 11 with it?
We're going to talk about Archimedes' principle a little bit, but the rest of it we're not going to really go into. I don't generally do 8 and 9. Well, sometimes I talk a little bit about 9, but I don't go into cohesion and adhesion in liquids. I know that it's a little bit interesting for people, but it's not. To me, it's something that if you're going to go into a field that deals with fluids, you'll learn about it. If you're not going to go into a deal that deals with fluids, you don't need to learn about it. It's not that essential. It just takes up time. So I don't usually teach it very often, but I do teach Archimedes' principle.
For engineers, specifically electrical engineers, do you do a lot with fluids or not really?
Not usually.
Except maybe with whatever fluid might be creating electrical current?
Yeah, but usually electrical engineers don't deal with fluids that create currents. They deal with metals that create currents.
Okay.
So it's not often the case. So, and you wouldn't need to know anything more than you already know. So, but Archimedes' principle is kind of a basic fundamental principle that we like to teach to everybody, and it's fairly straightforward. The idea is that here's the story of Archimedes. I told you part of it. I told you part of his story about how he died at Syracuse, the conquest of Syracuse. But earlier in his life, the main ruler of Archimedes, the king, not of Archimedes, but of Syracuse, the king there, had given some gold to one of his goldsmiths and asked this goldsmith to make him a solid gold crown. It was pure gold. He wanted a solid gold crown, but when he got the crown back, he suspected that the goldsmith had mixed some silver in with the gold and taken out some of the pure gold, replaced it with some silver, and retained the same amount of mass. You know, he took out a kilogram of gold, replaced it with a kilogram of silver. And when you mix silver and gold by melting it, you can't really tell by the eye. And so he came to Archimedes and said, is there a way to tell if this crown that he's made me is truly pure gold? If it was just a block of gold, they would be able to tell it. They would be able to tell because they understood how much a block of gold at a particular size weighed. But when it's all shaped into a crown, it's very difficult to figure that out. And so Archimedes was in his bathtub one day and discovered something. He discovered that when he put his arms down into his bathtub, there were some peculiar things happening. What kind of peculiar things happen when you have your arms out of a bathtub and then you bring your arms in?
Displaced water.
Okay, how do you know you displace water?
Because your bathtub either rises or
Okay, so the bathtub rises. And if the bathtub was completely full before you put your arms in, it would spill over, just like you said, right? And if it spilled over, how much water would there be spilling over?
Exactly how much water would fill the same space as your arms?
That's right. Turns out it's the same volume as your arms. And that's something that just kind of makes sense to people, but he started thinking about it. He said, if that water doesn't spill out of the tub, for example, when he put his arms in and it didn't spill out, then what does that water do when it rises up? So what are the other peculiar things that happen when you bring your arms into a tub? You ever notice that your arms don't necessarily sink to the bottom all the time? They kind of float, and if you don't want them to float, what do you have to do?
Push them down.
There's some kind of force holding them up. You have to push them down, right? Where does that force come from?
Buoyancy is the fact that your arms are less dense than water, right?
That plays a role in it, but that's not the thing that's pushing your arms up.
Normal force or surface tension?
Think again about the water that has gone up. What happens if you have a fluid that has depth to it, what does it create at the bottom of it? Not density, but pressure. And that pressure, when it's in a fluid, does it just stay at that one point, or does it distributes itself evenly throughout the fluid? We knew that from Pascal. So if you raise the height of the water by putting your arms in the water, your arms will feel what? Pressure. And the pressure underneath your arms will be greater than the pressure above your arms because of the slight difference in height, turns out. But regardless of that, it's going to feel this pressure because you've just raised the water by bringing your arms into the fluid. Now, the interesting thing about this is that if you have an item that has displaced some fluid that is less dense than the fluid that it has displaced, then that object will rise. The pressure, the forces on it will be enough to push it upward. If it's not, it will sink, but it will not sink at the speed that gravity wants to accelerate at, because that force is still there, that buoyant force is still there. And it will still push up on it. So it will slowly sink, which is what you see when you drop a heavy object into a swimming pool, for example. Right? So it goes in and it slowly falls to the bottom, much slower than it would in gravity. So the buoyant force is that force that is caused by that displaced liquid, that displaced fluid. Well, what is it going to be equal to? It's actually pretty easy. It's equal to the weight of the fluid that is displaced. The force that an object feels, that buoyant force that an object feels when it is either partially submerged or completely submerged in any fluid, is equal to the weight of the fluid that was displaced. And that can be for a gas or a liquid. In fact, it can even be in semi-solid, semi-liquid as well. But anyway, this is how submarines can float, and it's also how they sink. How does a submarine go underwater? It fills up its ballast tanks with water and makes itself more dense so that the buoyant force is not enough to keep the submarine on top of the water. And then when it wants to go back up to the top, it pushes all that water out of those ballast tanks and replaces with air, so that its density is now lower, so that the buoyant force is greater than the weight of the submarine, so it goes up to the top. Right? How does a balloon float in the air?
Because the helium's less dense than the air.
You fill it with something that is less dense than the air around it, so that the air that it displaces has more weight than the weight of the balloon that displaced it. And then that pressure that you've created by submerging this balloon in air causes the balloon to move upward. And an anchor works the same way. The buoyant force on an anchor is very real as well. When you drop an anchor, it drops slowly through the water. It's more dense than the water, so it does drop, but it drops more slowly. So you may not have ever heard of it, but they've made boats out of all kinds of things. Because how do you keep a boat floating? It's not because of the material it's made of. What causes a boat to float? What floats your boat? Because all you have to do is displace enough water that the amount of water displaced is heavier than the boat you put in the water, right? So they've made boats out of concrete, like honest to goodness real boats out of concrete.
Like full-size boats?
Full-size boats, shipping boats, yeah. They've made them out of concrete.
Aircraft carriers are basically made out of concrete.
Well, aircraft carriers are made of a lot of steel. But they do have concrete, a lot of concrete too. But yeah, I mean, they've made them completely out of concrete, completely out of all kinds of. But all that really matters is that you displace enough liquid, and they'll displace enough water, so that the water that you've displaced is has more weight than the weight of the boat that's displacing it. One of the things that people who are used to being around shipping understand is how to tell if a freighter is a full or empty freighter. How do you tell?
as it's in the water.
That's right. And they actually have lines on the hull so that you can tell. Right? So here is a freighter that is pretty much empty. Right? What does it look like when it's full? Here's another one that's obviously empty. What does it look like when it's full? You can't see that red line. Right? Let's see if we can see another one. I mean, they're just sitting way high in the water. They don't need to displace as much water because they don't have as much mass. The boat has less mass, so it doesn't need to displace as much water. You get them more full like this, and that red line is very close to the ocean. It can be even down below the ocean. They try to keep that red line above the ocean, but varying degrees. Let's see if we can see
Do they
it.
have like the boats?
Like here's one that's right down near the ocean, right there. Just full and full of containers.
So do they have like the boats kind of generally shaped somewhat like this, or in varying shapes, so that it can, no matter how much you load it with, up to its max load, like it will still float?
Shaped like what?
Like some of the boats up higher, not the one that was in the bottom left a minute ago, kind of like shaped like this.
Okay, so the reason for their shape is mostly for the hydrodynamics of the situation. However, if you notice down here at the bottom of the boat in the middle here, where it can be wide and still be efficient for going through the water, they make it as wide as possible. Because if it's as wide as possible down there, it will displace more water. So you want it to be as wide as possible at the bottom, but at the front and at the back it needs to be tapered for hydrodynamics. So that you get a nice shape of the water needs to cut through the water at the front and at the back. Because then it creates what's called what do they call that? They call that laminar flow. We'll learn about that in the next chapter. But anyway, that's Archimedes' principle: is that the displaced fluid is equal to the buoyant force that will keep this thing afloat. What does that look like mathematically? Well, here's what it looks like vector-wise. We have this, they're just showing a fake cylinder of water. A fake cylinder of water is held afloat in the same way. This water, within the water, it's not really an object of any kind, but it has a stronger force on the bottom because at a deeper depth it has a higher pressure. And it has a less of a force on the top because of the less depth, less pressure. And the buoyant force is the difference between those two forces, the difference between the forces created by the high pressure minus the low pressure at different heights. And if you put in an object in here, then you've got the weight of the object and the buoyant force that are going to essentially counteract each other. If the weight of the object is more than the buoyant force, then it's going to sink. If the weight of the object is less than the buoyant force, it's going to rise. If they're equal, it's just going to sit there in the water, and that can happen as well. But this is what Archimedes' principle is. The buoyant force is equal to the weight of the fluid displaced. It's plain and simple. However, the weight of the fluid displaced depends on the fluid, depends on the volume that is displaced, right? And it depends on, well, the fluid depends on the fluid's density, what kind of fluid it is. So the density of the fluid and the volume of the fluid that is displaced. So we often write it as volume times density right here. So the mass of the fluid displaced right here would be the density of the fluid, in this case water, density of water, and the volume of the water displaced. And that will you'll be able to calculate the mass of the water displaced, multiply it by g, and you'll get the buoyant force right here, and you're good to go. So in this case, we have 10,000 metric tons of solid steel completely submerged in water, right? So if you have 10,000 metric tons of steel, how much does it displace? Well, you got to figure out how much volume 10,000 metric tons is. You go find the density of steel in your book, it is there somewhere, or you go find it online. Turns out to be 7.8 times 10 to the 3 kilograms per meter cubed. You take that mass divided by that density to get the volume, and then you calculate the volume of the steel, which is 1.28, That's how much volume you're going to displace, and multiply it by the density of water, and that would tell you how much water you would displace, the mass of all the water you would displace. And the buoyant force is 1.3 times 10 to the 7 newtons compared to this is 1 times 10 to the 7 kilograms, which you'd have to multiply by 9.8 to get the actual weight of all the steel. So the weight of the steel is 10 times higher than the weight of the water that it displaces. So it's going to sink if it's just a big block of steel. However, if you shape this into a boat of some kind that can displace some volume, like this, they say that it can displace 1 times 10 to the 5th meters of water, meters cubed of water. Well, if that's the case, then the buoyant force is going to equal that volume displaced times the density of water, which is right here. No, right here. So the density of the water will be the same, but the volume displaced is going to be much bigger, 1 times 10 to the 5th. Then you've now got a mass of water that's 1 times 10 to the 8th kilograms, and your buoyant force is that times 9.8, and you get 9.8 times 10 to the 8, which is much more than the weight of the steel. The weight of the steel was, well, it's not much more, but it's enough more that it matters. So it's about 10 times as much. So it's significant. Then you can load it up with stuff. So, some things that you might want to use as you're doing problems. If you want to calculate the fraction of an object that is submerged, then it turns out that you take the volume submerged of the object divided by the volume of the object, and that will equal the volume of the fluid over the volume of the object. Volume of the fluid displaced. You can also turn that into masses divided by densities and use that as well. And then you can get fraction of an object submerged is equal to the density of the object divided by the density of the fluid. All very useful equations in doing problems. You'll probably come across something where they talk about the specific gravity of an object, and this is essentially whether or not it can float in water. So you take the density of an object divided by density of water, and that tells you the specific gravity. If you have a specific gravity that is less than 1, then you float. If it's greater than 1, you don't float. And if it's 1, you just are neutral. You neither sink nor float. So,
So if you neither sink nor float, are you on top or are you submerged?
you're not on top. You could be just below the surface. To be above the water, you have to have a specific density that's less than 1. But you could be just below the surface, or like right at the surface, and you're completely submerged, or you could be lowered down, or whatever else. You could be anywhere. So here, they're having you calculate the density of a woman to see if she's going to float. Let's see, 60 kilogram floats in fresh water. Oh, so they're actually telling you that she floats with 97% of her volume submerged. So they're telling you the percent of her that is submerged, and they're telling you the mass, and you're going to use one of those equations to calculate the average density of her body. Here they show a device that actually tells you what the density of your body is. So you've ever heard of people saying, I have so much percent fat in your body. They can tell that by doing a test like this. They can measure the density of your body. They do some approximations as far as bones are concerned. If they really want to be very thorough, they'll take an X-ray of your body to figure out how big your bones are and how dense your bones are, but usually they don't. But that's one device that they can use for that kind of thing. You have to blow all the air out of your lungs to get it done. But here is the experiment that we're going to do, which is an experiment that Archimedes did. Because once he figured out this idea of the buoyant force, he came up with an idea. And the idea has to do with that woman who was partially submerged, or anything that gets submerged in water. If you submerge something in water, you can actually, and weigh it while it's submerged, you can actually figure out the density of an object. And that goes for crowns. If it's solid metal, if there's no gaps or holes of air in it, and you submerge it, you can figure out its density by comparing its submerged weight with its non-submerged, its weight in water and its weight in air. And that's exactly what Archimedes did. And as the story goes, once he figured this out, he jumped out of his bathtub and went running through Syracuse saying, "Eureka!" which means "I found it" in ancient Greek. And he was naked, running through town. So that's why, if you see pictures of Archimedes, you see him running with his big beard covering his naked body. It's almost always the way. But anyway, just kind of funny. So, this is how it goes. If you weigh yourself out of the water and then weigh yourself in the water, and you take the difference between those two weights, that will equal the weight of the fluid that you displaced while you're doing it, while you're doing that experiment. Or the same thing for mass. The difference in mass is equal to the mass of the fluid displaced. Well, once you've calculated the weight of the fluid displaced, then you can use that in one of these previous equations to calculate the density of the object. Right? And that's a beautiful thing. So that is buoyancy in a nutshell. So let's do an ancient Greek coin here really quick. Let's do Archimedes. So the mass of an ancient Greek coin is determined in air to be 8.630 grams. When the coin is submerged in water, its apparent mass is 7.8 grams. And we want to calculate the density. And if we calculate the density, we might be able to figure out what it's made of. So to calculate the coin's density, we need its mass and its volume. The volume of the coin equals the volume of the water displaced. The volume of the water displaced can be found by solving the density equation. Density equals mass over volume for V. So we do that. Volume of the water is mass over density. And the water displaces a mass of, let's see, so we take the difference in the difference of the coin out in air in water, and that ends up 8.63 minus 7.8, and it's 0.830 grams. So that's how much water we displaced, just barely a gram. So the volume will be equal to that mass divided by the density of water, which is 0.830 cubic centimeters. Then that means the volume of the coin is the same as the volume of the water it displaced. So we use that volume and then the mass of the coin outside of water. Here's the mass of the coin outside of water. Here's the volume that it displaced. Divide those two, and we get 10.4 grams per centimeter cubed. It turns out that that is actually the density of silver. So you can calculate, you can determine that that is a silver coin. And you can do this to a very high degree of precision if you have a good scale. You can also do it to a fairly high degree of precision if you just have a good balance. So in this case, they're just using a balance where they have a known mass here and the unknowns on the other side. Right? So either way it works. So that is Archimedes' principle in a nutshell. And we're going to do a lab with Archimedes' principle. Let me go and get the lab. I can't remember if it's in here or I have to print it off. I have to go print it off really quick, so I will be back. I'll be right back. Okay, did something goofy when I copied them, but it still works. Yes. So here's the lab, and every other page is blank. I don't know why I did that, but all the pages that are supposed to be in there are in there, just every other one is blank. So the way this works, the way this lab works, is they use a triple beam balance. We're just going to use our force transducers. And the way this works is you put your force transducer, your force measuring thing, on a stand, and you hang the masses from it in air to measure their weight, and then you put them in a like a graduated cylinder to measure the weight. And as they are put in the graduated cylinder, you can see the change in the volume in the cylinder. And they have you using like a pipette to exactly get, an exact amount in your graduated cylinder. I don't have pipettes, and I don't think it's all that necessary. You can use some eyedroppers, I guess, if you want to. Have you guys ever had a chemistry class or something where you're talking about the meniscus, where when you put liquid into a container, the surface tension of the liquid makes it adhere to the side of the container on the edges there, and so you get this little kind of smiley face, and you want to measure to the bottom of that curve because it comes down to a curve. You want to measure in at the bottom of that curve. But anyway, they talk about in there just so that you can measure exactly how much water you have before. Cut my head in there. This big old lump on my head. Anyway, I've got. I'll get you a graduated cylinder. You guys can all work together on this. And then you hang some masses in there. I've got those for you, and I'll get those out to you as well. And then, let's see, what else do I use? We can measure the volume two different ways. You can measure the volume before you put in the thing and then watch it rise. Or you can actually, you can fill a container to the top, all the way to the top, and then put it in and let it overflow into a catch container, and then measure it separately. And I don't know, I think I like to just watch the change in the cylinder. It makes more sense to me. First thing you need to do is we'll need to get a bar clamp and everything set up on your table so that you can hang your force transducer. You know those force things that we use in the force probes? There's actually a table clamp and a bar here. You guys can use. You want to thread it along the bar.
This one right here?
No, up here. One of these.
Oh, that's like
And one of those. East of the clamp. So clamp that onto a table, wherever you're going to do it. Maybe that back table will practice. There's no more room there. And then the bar goes on that side. You actually might need to screw it. Into your graduated cylinder.
Just want to use a stick. backer?
Yeah.
Or are we gonna put it down here?
I was just gonna set the block over here.
I was thinking we could use that.
Oh, that works good. Probably set it more stuff.
So here is a graduated cylinder. Each of the markings on here is 5 milliliters. There are some different materials you can use. I think they have to do a couple of different ones. See what else you need. Looks like you have 2 medicine, we use plastic instead of wood. And to stick, to get those on there, just use some tape, just tape it on. That's the easiest way. That new caliper around. So I'll get you a new caliper and the force. Here's this. I'll get you across kind of too, so it'll go the right direction. You don't want to put it on that way.
Tape.
Where's the tape? In my office. On my desk. Probably. Let's see here. There you go. So now you should be able to measure the weights. And you're going to just so with a piece of tape on that. And then let's go to the two down here and put the weight on here, and then you have to have that full, looks like it's
Black and gold.
So we've got some other metal. All right. I think that you're good to go. With that. If you have any questions, I will be around, probably in my office, but
Is there a zero?
you can zero it in Lab Pro. Go to experiment.
Okay.
Well, since it's coming, we're on zero right
No, you want to zero it with the,
now. Okay, go to zero. Ready?
Now make sure you're reading through loud and you're going through the procedure one thing at a time, not just going. This is working, you're getting good values. Right? Okay.
So we're supposed to measure the outputs and weight and variables first.
I've got one. We're double checking. Find out.
Okay, so what are we going to set the goals?
That's our plastic one, right?
Yeah.
So we're gonna do that with the white ones. We have like two metals.
Huh?
We have two metal cylinders. We're gonna do the.
Okay, so we want to come back to that one?
Come back to the plastic cylinder.
Yeah.
Yeah.
Okay. Now, do these? Which one would you like using now?
Copper. Yes. Steel.
Brass. Excuse me.
Both of them.
This one. Yes. In some places, it's more expensive than the other.
Saffron is what 10 times its weight equal. Well, rather than an answer, but it's nice.
Oh, yeah. Okay, you want to go ahead and zero that?
About 550, 0.55. Okay.
So we're measuring force. We're measuring its weight, so we're measuring backtracking mass, right?
We don't have to do mass. But like we could, but we could also just do the difference between the forces. Because we know our levels can have consistent mass. Okay. And we know our subject is going to change. I really hope that its mass is not changing a lot. And instead of
Possibly be very rich. It's changing its mass, so it's
work decreasing.
so it decreases yourself to the north rate, vaporization. Increases, you open up a company.
Oh, shit. Heat.
Yep.
Actually, if its weight's decreasing, I think its mass is decreasing. I'm going to find out why its mass is decreasing. And then use that, especially if it's small reduction, use that to go faster with boats and airships. Okay, so sci-fi is my thing. Shoot me.
Have you ever heard of indexes?
Yes. Because, first of all, both my parents are not so good at the game. Second,
I played it for the first time last night. I didn't see it driving home at 1 a.m. Slipped away. Let me tell you, playing a horror sci-fi game and driving home at 1 a.m. Probably never stop at your dad's office and buy a river in the way. Not fun.
I just had this really sick inspiration.
What are we going to do?
Automated restrict, and then you can take them outside of this. Take them off on the outside. So if it does start hanging down, or catch up with it. That's the key. That's simple. Have you played Silent Hill?
No.
Are you playing? Oh, okay. Generally considered just about the scariest puzzle solver out there. It's not jump scare, it's thrill. So the entire time you know something's coming, and you're just always waiting for something to say that one. And I've not played it, but I've seen most of the things they throw at you. Well, also there's the enemies that you're supposed to fight things, but you never get one. Sometimes you can use IVs, and for the most of that happens inside hospitals.
You want to go out and do it? Try this again.
You get like IV stands and E-pod. You know, it's skeletal, right? And none of them have information, and then all those great.
Something right around the center. Try to shove it into the water.
Yeah.
How much water do you 200?
Well, how high is this thing?
You can only go up.
This string?
I would put 200.
Okay.
Well, the thing about this is like the first time you ever encounter one of the enemies, it's kind of freaky because it's like, imagine, have you seen the movie Ant-Man?
Most of it, not all of it. Apart from it.
You know, like the bad guy who has like in the yellow jacket suit?
Yeah.
Imagine one of those, like with the spikes, you know, that come out, except the one actually like there's some shoulders. Yeah. So it's really freaky at first because you don't have any weapon to fight them, but then anytime one of them appears, the music changes. So it's like, oh, what's gonna happen? Yeah. That's like, I can see supply over there. I'm gonna walk through this dark hallway. I feel like I'm going once about nothing.
It's fully submerged.
Awesome.
And it looks like we raised about 7 milliliters.
Are you supposed to instrument forces for a first one?
Yeah.
Okay. We're sitting at about
500.
495. So, okay.
What was the second Sir, please get off. Please get off. Making stupid comments. Just something to break the sheer. Humor is a great defensive sport.
That is. Okay, so we have our 1.05, right?
Yeah. Okay.
So the bug procedure and calculate average, what's this about?
So they want us to do the experiment completely again from start to finish. And then check our, basically we're gonna, I also got 100%. Ready? Okay. 0.
First, what do we first have,
Yeah. I see 557.
Let's do that one. Zero.
Okay. Okay. What we got? 485.
That's 480.
Okay. .0675.
That was what I meant. Does that sound right?
Yep.
I don't agree with this, but there's plans on it.
Oh, I just had a not agree where I could take special. Okay. Who does actually study and pretend? We all look for grades and calculators, but most people only see two grades and calculators.
That's this and that, Cassio?
Most of what I've seen is HP Texas. I think so the ones that standardized for the ACT and safety. I've not seen Casio Scientific before. I've only seen their all calculators. I found that
Okay, what was your impact?
interesting is the cost of that. Disclaimer, no, I'm not being judgmental. Just easily entertained by interesting observations.
I've seen 477 inch phones.
What is that?
Yep. I'm sure it's zero income.
You'd be really upset if this is like 40. No, it's not. I would upset you greatly.
Okay. Yeah, I just saw 2014 for you.
What did you go? 0.054.
Same here. Okay. 0 for use like any towel, also named shirt.
Oh, right. A couple of drops of water on that. Scientifically.
Yeah, it got on 486 for a long time, it keeps coming back. I think 486 sounds good. So,
What's the first one for the stress?
well, since the weight was so much, she's kind of watching to see which one it itself. Oh, it was good.
Now wait.
She might want to do it again. When she's on fish.
It zeroed out at negative 10 meters, and I was like, Wait, 421, I've seen it like 3 times.
Zero six five.
Yep.
Zero 595.
Yep. And that gets us to experiment 2. It gets us to part 2. Now they want to calculate volume.
We want to do it about precise, so we just go with the fact that it's really close to the 195 line.
You complain about this scientific accuracy? Good, because I don't exactly. Hey, there's precision and there's accuracy. I will keep precision being the way I would, but I'm not going to do that.
Okay. So we're supposed to jump in, or so let's also move in. Well, the new water level calculate the change in volume. This is the equation. This is the volume. Calculate the rate, space, and all that. For 195, right? I'm just going to drop this. I'm 201.
Don't see a 201.75.
Okay, so 201. So the volume of the space water is 6 milliliters. And the equation now. What is equals density times the volume times gravity? It's rho VG, right? Rho.
Rho volume times gravity.
Okay.
So, rho is density volume.
So, let's see, it's about volumes reduced to volume 6 milliliters. Gravity. So, all of this just comes out to me, but that's our unit.
It should turn
So, just 1,000 times 6 times 1, right?
Oh, okay, I see.
What would be wrong?
So, we are density is given in kilograms per meter, right? We measure volume in milliliters,
Which is grams per centimeter.
right? So we need to convert that to kilograms per meter.
Which one do you want? Which one do you use? I would guess kilograms.
As long as we have the same unit, yeah, as long as we have the same unit, it should not work.
Okay, so how do we go from kilograms to meters cubed? From, should I have gone from 1,000 kilograms per meters cubed to grams per centimeters cubed? It's going to be easy to talk, right? I know our units are huge, but I don't know what to do with these.
Because what we're doing is we're taking, someone would remember metal. And we're trying to calculate its density using different methods, but we can bring that up here and we did right here in prior lecture. I know that's our end. I'm just not 100% sure how to get. Because it should actually, I think it should come down to, let's see. If you look at our average boiling force, it's already basically the same as the water display. We're getting pretty close.
Okay, okay, just equals 1 gram. 1,000 kilograms per meter cubed equals 1 gram.
Okay, so it's just one. Yeah, it's times one. Okay. That makes sense.
So, we do something wrong in the first procedure.
This actually, if we're calculating volume times density, did we ever?
Should we have essentially measured multiplied times sometime in the first procedure? Exactly. What's your measuring force?
They would have had to, because they use a triple B now to measure max, right?
Yeah, so we don't have to multiply times gravity.
Not even matter. That's my goal. Does that make sense? Because if we do that, that puts our numbers correct.
No, we're just at 6, right?
We're at 0.06.
I'm sorry.
Because we're at 0.0 milliliters. 0.06 milliliters. And our number up here, of course, times.
How did you get 0.06? Because it's just 1 and it's 6 milliliters.
Oh, I'm measuring in liters. That's why. I was doing it in liters. That's why my units are working.
Well, I'm still way off because even if we use the 1,
Divided by 1,000. Because that puts you back in liters.
okay, why don't we do a liters?
Because liters are comparable to meters per kilogram. That because it's meters per kilogram that you can compare directly to liters.
Okay, so I get,
Does that make sense?
yeah, so
I believe that's correct.
6.
Because the metric system is based on water, compared to water ratios of 1.
Take a shot. Force of buoyancy, the force of buoyancy got on the first one was 0.05. The average was 0.0675 from being 0.006 divided by 5,000.
And it's 100.
No, let's do that.
Okay. Andrew, I figured it out. What did we do? We still need to multiply by 9.8 still. My issue with it was I had knocked off one of my zeros between this map and this map without realizing it. So times 9.8 will bring it up to more or less times 10. And that will bring it almost exactly to
Okay, so
So
explain
it's
what
time.
I'm doing. So for my density, what does that need to be? Does that need to be grams?
10. Kilograms per meter squared.
So it needs to be 1,000?
Well, only if you were using, you're still using milliliters, right?
How about I do this? So 6 milliliters would be 0.006 liters, right?
Yeah. So now you just took up to 1,000. Now you can multiply by 9.8.
Okay, so I'm
Are you following my twisted logic?
so 1,000
Okay.
times 0.006.
So we had volume initial, volume